Linear programming is a specific type of optimization which actually arose in the early 1900s in the military. In optimization, we're usually trying to do one of two things. So first of all, we might be trying to maximize a quantity. That might be like trying to make the most amount of money in a business. Secondly, optimization might be centered around actually trying to minimize a certain quantity, like we might be trying to, say, reduce our energy consumption. So those are the two main things you're going to see in any sort of an optimization problem, maximizing or minimizing a certain quantity. So we're going to see that in linear programming itself here. So let's get into this. So it does say that a furniture dealer is setting up a showroom of tables and chairs. He has a budget of $90,000 to be able to spend and enough space in that showroom to be able to fit at most 300 pieces. Now it's going to cost him $750 for a table and $150 for a chair. And of course he's going to mark this up a little bit so he can make some money. So he's going to be able to actually profit $100 off of the sale of each table and $30 off of the sale of each chair. So with all of this, we want to be able to determine the number of tables and the number of chairs that the dealer should purchase from his available money to be able to maximize his total profit. So ultimately his goal, right, is he wants to make the most amount of money as possible, right? But there are some confines that he's limited to here because of budget constraints and also because of space constraints. So what we really want to try to do is we want to try to find the sweet spot. So in other words, like what is the exact number of tables and the exact number of chairs that will stay under budget and that will also fit in the showroom that's going to make him the most amount of money. And so in any sort of an optimization problem like this, okay, looking at this graphically is kind of going to be a big thing for us. So you'll see off to the left here a number of different things that we're going to need to consider in any sort of a problem that can be modeled with a linear programming type of problem. Now, first of all, you just see here it says to define variables, which you want to do in any sort of a problem where you have some unknowns. And so in this particular problem, I think we have a couple of unknowns because, for one, we don't know the number of tables, nor do we know the number of chairs that the dealer wants to purchase. So I think we'll define those accordingly. So we'll define, let's say, a variable x, and how about let that be the number of tables that the dealer is going to purchase, and then we'll define y, and how about if we let that be the number of chairs that the dealer is going to purchase. All right, so now the next thing, this is kind of a really big one right here when we're dealing with what we call the objective function. So an objective is what you're trying to accomplish, right? Like it's your goal. And so in this situation, this dealer's goal is to, of course, figure out the number of tables and chairs, but ultimately that's going to help him hopefully maximize his total profit. And so our objective is to really make the most money out of our profit. And so I'm going to define something that's going to be called P. And so P is going to stand for the profit. Now, to be able to determine his profit or the amount of money he's going to be able to make, it's going to be taking, of course, the number of tables he sells, but then times the profit he's going to make off of a table. So recall that he was going to make $100 off of the sale of each table. And then we're going to, of course, add that to taking the number of chairs and times in that with the profit per chair there. So when we do 100 times x plus 30 times y, then that's going to equal your profit, as it says. Now, we don't want to just let that alone be the objective function. It's not just about the profit, but it's about being able to maximize it. So whenever we specify an objective function, you're going to see most of the time that it's not just the function itself, it's also, are we trying to maximize that value of the objective function, or are we trying to minimize? And so that maximize word is a critical component of what we're seeing there. So next, we want to consider what we call constraints. And what constraints are just limitations in a particular situation. And in this particular situation, there were a couple of constraints that were specified. The first of which was that he had to stay under a $90,000 budget. And so by taking the number of tables, we know that he's going to have to spend $750 per table, and then he also has to spend $150 per chair. And so then if we take 750 times x plus 150 times y, that's going to amount to the total amount of money that he spent to purchase all these items. And we need that to stay equal to or underneath $90,000 overall. So that's one constraint that we want to be able to consider here. The second constraint is that the showroom can only fit at most 300 pieces. So that means that the number of tables plus the number of chairs, that would give you the total number of pieces, needs to be equal to or needs to stay under 300 overall there. So that's our constraints. It actually forms a system of linear inequalities. And so using this system of linear inequalities, we're actually going to now graph these constraints to look and examine and see what's actually possible in terms of combinations of x's and y's here. So on the graph here, I'm going to go ahead and specify this to be our x-axis and this here to be our y-axis. So recall that this really is going to tell us the number of tables on our x-axis, and then the y-axis is actually going to tell us the number of chairs. I think I'm going to count by 20s, so that means that's going to be 100 tables, and 200 tables, and 300 tables, and 400 tables, which of course we can't have 400 because we can only have 300 total pieces overall. All right, excellent. Okay, so there's a couple conditions here, so I'll try to use some colors so we can kind of correspond things here. So how about if we try like this purple color right here for that first constraint that we're seeing there. So if I wanted to graph that particular constraint right there, it's a linear equation, and so it'd be nice if we solved that for y. So if you do subtract 750x from both sides of that and you divide by 150, what you're going to get out of that then is it's going to be equivalent to the fact that y is less than or equal to negative 5x plus 600, which then if it has now a y-intercept at 600, it makes it not so easy to graph on this graph because 600 is a little bit too high for us. So maybe let's try to find the x-intercept of this. So if I want to find the x-intercept of this, that means that the y-coordinate would be 0. So if I were to actually like plug in a 0, then in for y right there, and then solve for x, so divide by 750 on both sides right there, what we're going to get then is we're going to end up getting that x has to be equal to 120 then. So that means that 120, which is going to be right there, is going to be the actual x-intercept. And then because when I made this graph, I made the scaling of the x and the y's be exactly the same, then it does turn out that if I use this -5, then I can just kind of go at a -5 slope like you're seeing here. Oh, I went off a little bit there. Okay, so something like that should be a little bit more accurate. So if we kept going, eventually it's going to have that y-intercept up there with 600. So we're good there. So I'm going to actually make this a nice solid line, and that's going to be that first constraint there. For the other constraint here, so let's use, I don't know, like this yellowish right here. We've got that x plus y has to be less than or equal to 300. I think we'll be able to fit that on our graph because that's equivalent to the fact that y is less than or equal to negative x plus 300. So we can get 300 for a y-intercept right there, and then if it just has a -1 slope, then we can just go at a -1 slope like you're seeing right here. All right, so what we also want to now consider is a couple of other aspects that I haven't specified as constraints but are just as equally important. So you'll notice that I kind of have a graph that only really is in the first quadrant of the Cartesian plane, and that's kind of just because we can only have things in the first quadrant, right? Because otherwise, if we were in other quadrants, we would have negative number of tables and negative numbers of chairs. So there's a couple of constraints that we should also add to this list. So there's actually going to be like a total of 4 of these. And the first of which would be that we can never have a negative number of tables, and the second of which is that we can never have a negative number of chairs. And so those there are equally important aspects of what we're dealing with when we're dealing with situations like this. So because of that, then I guess the x is greater than or equal to 0 sort of line is going to be this y-axis really, and then the fact that y is always not negative is going to be kind of like this x-axis right here. So it turns out then that based on all of these inequalities, if we were then to do some shading so that we go to the right of that x is greater than or equal to 0, and we go above that, and then right here we go below that, and we go below that, it turns out then that we end up getting this region right here, which is kind of actually like a quadrilateral type of region here. And so what we denote this region here to be is we call this region here the feasible region. And so by feasible, the word feasible means possible, or these are our possible options. And so what's meant by that is that any point within this particular region, I'm just going to pick like a random point, like that point right there would happen to have coordinates like 40 to 20, for example. And that would be one possibility that's going to satisfy all of the constraints, meaning that it is having an x-coordinate greater than or equal to 0, and it has a y-coordinate greater than that. But not only that, but it's going to stay under budget and also have 300 pieces or less. So that gives us our possibilities, meaning then that within this feasible region, we're going to be able to find somewhere that's going to give us the maximum. Now, it just turns out that when we have a completely bounded region like we have right here, in other words, it just forms some sort of a closed geometric shape, in this case a quadrilateral, then both the maximum and the minimum to the value of your objective function is actually going to occur at one of the corner points of this particular region. And by corner points, we're meaning either that corner point right there of 0, 300, or that corner point down there of 0, 0, and this corner point over here of 120, 0. And then we've got one more corner point, which is occurring right where the blue and the yellow line are meeting right there, which we don't know exactly where they are at. But is that something that we may be able to find? And it certainly is, because if the yellow line that we know is y is less than or equal to negative x plus 300, and then we also know that the blue line right there is y is less than or equal to negative 5x plus 600, then because now they're solved for y's, we should be able to find the x's where they meet each other if we set negative x plus 300 equal to negative 5x plus 600. So if I get my x's all on the same side, and then the numbers on the other side, we divide by 4, it turns out that x would have to be 75, where those 2 points meet with one another. So we know that that red dot right there is going to have an x-coordinate of 75, and then we'll need to plug in a value of x into one of them to be able to find the y. So if I plugged in 75 for x right there, then negative 75 plus 300 is going to give us 225 there for the y. So those 4 red dots form our corner points, or in other words, corners of shapes are often referred to as vertices. And so with those vertices then, we're going to be able to find the minimum as well as the maximum of our objective function using these particular vertices. And so using these possibilities now, all we just need to do is then evaluate these underneath the objective function, or using the objective function to see what values we get for profit. So with that first vertex, if we plug that into the profit function, in other words, if we take 100 times the number of tables plus 300, or plus 30 times the number of chairs, we end up getting $9,000 in profit if he had bought 300 chairs but no tables. Now this one's kind of interesting, because if you buy no tables and then you buy no chairs, he's going to make 0 money. So that actually will end up being the minimum value of his objective function. So that's the smallest profit he'll be able to make if he buys nothing, of course. And then if we do 120, so $100 for 120 tables plus $30 times 0, that's going to yield him $12,000 in profit. And then finally, if we have $100 for 75 tables plus 30 times 225 Let's see. So the first one's going to be 7,500. The next one's going to give us, let's see. So we would get 6,000, but then we would also get 7,500. So it should come out to be 6,750. And then if we add those together, it's going to be 14,250 overall there. So now if we compare all of those values there, you can see that the highest amount of profit he's going to get is that last one right there of $14,250. So we know the maximum profit that he could ever make is $14,250, and that's specifically when there are 75 chairs and 225 tables that were purchased.